The next talk is joint work by Filippo Moro and colleagues, joint work from University of Zurich, ETH Zurich, IMEC and KU Leuven, and CEA Leti in Grenoble.
Great.
So we are very much looking forward to your talk.
Thank you. Can you hear me? Great. All right, so let me start by being very, very thankful for the opportunity to be here on the stage. Let me also be very, very thankful with everybody who participated in the MScale European project. I see many of the participants here. And in particular, let me be very, very thankful with the people you see listed here for helping me putting together the presentation. So I will tell you about a device-enhanced substrate for multi-time scale processing. And let's start by defining what multi-time scale applications are. So these are edge processing use cases where information spanning multiple temporal decades is processed in a streaming fashion. And let me give you 3 examples to be more concrete. So let's take speech processing, but not just at the keyword level, but at the conversation level. Or maybe biosignal processing, but not just at the single heartbeat, but really monitoring the state of the patient for multiple days. Or perhaps robotic navigation that spans minutes or hours or even days. And the constraints that these applications impose on the hardware are that the hardware has to be low power, it has to be low area, always on, and because of the nature of the multi-time scale information, it has to have low latency, so fast responses, but also long memory. So let's see what is a good hardware substrate for these types of applications. So we divide the types of hardware substrates based on the algorithm that they're running. And on one side, we have artificial neural networks, and on the other side, we have dynamical systems. So let's see, and by the way, we use mainly electronics. So the possible choices for this hardware substrate are either digital or analog. And we want to analyze the pros and cons of each of those subcases. So for artificial neural networks in digital electronics, they are easy or easier to design. They work very well. They're probably the state of the art in terms of the algorithmic performance. They can profit from advanced CMOS nodes, but as we can probably agree on, the advancements of CMOS technology is slowing down a little bit. And also, this architecture are mainly volume normal architectures, and so they suffer from large data movement. This is partially addressed by mixed signal implementation, where the matrix vector multiplication operation is performed in the analog domain, and everything else is in the digital domain. And this makes such a substrate more energy efficient, but it also introduces analog to digital conversion as an overhead. And it also makes such hardware more difficult to design. On the dynamical system side, we have, again, digital, which is easy to design. It's energy efficient, but mainly because of the underlying algorithm that is running. That could be, for example, spiking neural networks. It can use advanced CMOS, but again, there's the slowdown of Moore's law. And also there's the aspect of the simulation of a dynamical system that introduces some imprecision in implementing the algorithm. So for example, we could also use an analog substrate, which is very energy efficient. We have the bonus of the emulation of the algorithm, so time represents itself in analog. But we have the problem of limited time constants, and also the problem of mismatch. And we can all argue that it's way more difficult to design. So across the board, we also have the fact that because we're using electronics, because we're using silicon, we also suffer from silicon leakage, and thus we have static power consumption. So through the MScale project, we tried to analyze the hardware substrate mainly on the right column, so under the dynamical systems side, and in particular addressing the limitations of analog. So again, we have 3 main problems. So static power consumption, limited dynamic range, uptime constant, and mismatch. So we all know that static power consumption can be addressed with the use of non-volatile memory devices. I don't have to explain you what they are, but why do we want to use them? Well, it's because the main other memory device that is available on chip is SRAM, and we know that SRAM scaling is slowing down, as it's been beautifully illustrated by this figure in a recent Shimiyu paper. So going from 5 nanometer to 3 nanometer technology, the advantage in terms of density of this SRAM memory is very marginal. But also, at the same time, non-volatile memories are getting better in terms of density. They're getting competitive despite the disadvantage of the underlying technological CMOS node. And then the very obvious advantage, which is the fact that they are non-volatile devices, so they help in reducing the static power of our chips. They're also multi-levels. So for example, RRAMs, PCMs, and VRAMs can store up to 3 bits of information in a single cell. And we know that these devices, we can aggregate them into crossbars, and we can perform the matrix vector multiplication, and so do great in-memory computing. But maybe I'm not the best person to tell you how to do great in-memory computing, but I can definitely tell you how to ruin it, for example. So what is one of the challenges of in-memory computing? In my opinion, is to optimize the peripheral circuit. So let me tell you how peripheral circuits can really ruin in-memory computing. And by the way, peripheral circuits, we need them to read the state of these devices and in fact perform the multiply and accumulate operation. And we would like for those circuits to be small, but also to consume a lot of power. So for example, you could design a circuit that looks like this one. So it's based on an operational amplifier. And it was my first attempt in designing some peripheral circuits. But the problem is that this operational amplifier is bulky and inefficient. So it leads to very high static power consumption, which we don't want. But luckily, there is a solution to this problem, as it's also been illustrated by Professor Kallenberg this morning, to utilize a charge-based approach and accumulate charge on a capacitor. And this has been thoroughly demonstrated to reduce the static power consumption, but also the dynamical power consumption for reading out the state of our memristors. But the beauty of a fully analog substrate that is running a dynamical system is that we don't even need to perform the analog to digital conversion operation. Once we have performed the matrix, the multiply and accumulate operation, we can get rid of this circuit and replace it with a analog neuron, for example, for computation. All right, so this is how non-volatile memory devices can help reducing the static power consumption. Concerning the second limitation, which is the limited dynamic range in time constants, we can use another type of devices, which is the thin film transistor type of device. So again, we have a problem in that we want to reproduce a large range of dynamics in our dynamical systems to tackle multi-time scale applications. And silicon is very good for fast, but is not very good for slow. So how can we make our neurons, our computational elements, slower? Let's consider a circuit which is a very simple neuron circuit, which features a capacitor on which we accumulate charge, and thus we'll have a certain voltage. And there's 2 transistors here, which represent 2 leakage paths for this capacitor. And in particular, this transistor here, M1, is the transistor that controls the current with which we are discharging this capacitor. And so to make very slow dynamics, we would like this current to be indefinitely slow, indefinitely small. But unfortunately, we cannot make it as small as we would like because we are limited by silicon's leakage. So we went on to analyze what's the off-current density in different CMOS technology for different transistor types. So for example, the core transistors are the smallest option in a certain technology, and the HV is the high voltage option. And you can see that going from bulk CMOS to FDSOI, so fully depleted silicon insulator technology, can help you in reducing the off-current density by about 2 orders of magnitude. And this takes you from some tens of milliseconds for this circuit to about hundreds of milliseconds or maybe a second, but it's not long enough, right? So one way to get lower in this graph is to utilize a particular technology, which is the IGZO, and you can make transistor with this technology, and you can really lower the off-current density by 5 orders of magnitude, as it's been demonstrated by my colleague in IMEC. So so I want to acknowledge Mauricio Velasquez and Frankie Cator, who built a neuron which is based on this TFT technology, and by doing this, they achieved a time constant, which you can see here plotted with the black dots, of up to 100 seconds, so extending the range of capability of silicon. And this is how we can get a much wider range of time constants in our circuits. Okay, so we have solved point 2. What about point 3? We'll see later. But for the moment, we went on to see whether these technologies that we are proposing even are competitive compared to digital hardware. So thanks to the help of Zhu, we designed a very simple digital chip that is implementing a spiking neural network. So it has this simplified architecture that you can see here. The specs of the chip is that it's been designed in 28 nanometers technology with 128 neurons. It has an SRAM bank of 16K for the weights and a neuron register of 8K bits. And Zhe performed some post-layout simulations of this chip. And this is the power breakdown. First of all, it consumes about 11.6 microwatts, which is already pretty good. And most of the energy goes into reading and writing the buffers and the memory. So we come back to this problem of the von Neumann bottleneck. And we went on and we tried to design a similar chip utilizing the technology that I just mentioned. So we use 22 nanometers as the CMOS underlying technology. And then we feature ARM and TFT neurons of the same size. So we basically have designed a system that is really equivalent to the digital one. And we have estimated through simulations and measurements the power consumption of such a design, and it turns out that it's a little bit better than the digital counterpart by a factor of 3. But there is still a lot to explore because, in fact, the colleagues who've put together the TFT-based neuron did not really push the design to the low power direction. So there's still a lot more to explore, and this is why we think that this is a promising avenue in improving the analog substrate. Okay, so to summarize, I've shown you how non-volatile memory devices can improve static power consumption. I've shown you how the limited dynamic range problem can be addressed with thin film transistors. And I've also shown that this device-enhanced analog substrate is competitive already compared to digital synchronous architectures. But there is still a lot to do, right? In particular, there's still the problem of mismatch and imprecise computation, which we think can be addressed by co-designing algorithms and hardware. And this leads to a call for action. Because obviously, all of these promises of analog memory computing can only come true if we do the following. So obviously, we need to keep improving the memory technology, so keep building better memory devices and transistor types. But it's not enough, right? Because at the end of the day, we also have seen how important these peripheral circuits are for memory computing, so they can really hinder the efficiency of this approach. And on the more algorithm side, we need to try and make use of this low dynamics that we can now produce with this TFT-based neurons for multi-time scale applications. And again, we need to do hardware and software co-design so that the algorithms and the hardware can meet a little bit in the middle and produce very efficient electronics. Okay, so let me conclude by acknowledging everybody who has been helpful in discussing this this presentation, and all the collaborators in the Institute of Neuroinformatics, CLAT, CSIC, CNR, IBM Zurich, University of Groningen, IMEC, and ICNCE. Again, let me be very, very thankful to my collaborators in the MEMScale project, and thank you for your attention.
So, thank you very much for this very nice talk. Please, for questions, come to the microphones.
So, Martin Lefebvre from UC Louvain, Belgium. Thanks for the nice talk. I was interested on how you interface your TFTs with your digital part of the system, because usually TFT, or at least pragmatic, it's only NMOS and it's on a flexible substrate, but you mentioned 22 nanometer, maybe FDSOI, I don't know. So how do you co-integrate that?
Yeah, for the moment, we haven't done that step. This is obviously something that we really plan on doing, especially the colleagues in IMEC. Yeah, it's to be discussed, so I don't have any more details to give you. So definitely feel free to contact Mauricio Velasquez in IMEC and Frankie Cutler, and they can definitely give you more details about this.
And maybe another short question, if I may, related to that. So does the power consumption of the IOs between your 22 nanometer chip and the TFT is accounted for in the power consumption that you report?
No. The IOs are not accounted for.
Okay, thanks.
Are there any other questions? Then maybe one question from my side, a bit more from a layman's perspective. You mentioned the importance of making the peripheral circuits more efficient. How much more efficient would they need to become? And is it just a design issue, or would new technology also be needed there?
So considering how much more efficient, it depends a lot on the design. So I would really rely on what Professor Kauenberg presented this morning. So I guess the objective is to go beyond what the human membrane is capable of, so performing synaptic operation below 1 femtojoule. It's definitely possible. I think if you walk around the poster area, there is I think I want to acknowledge this poster, which is about charge-based in-memory computing. I think they go below this 1 femtojoule mark. So there are ways to make these operations very, very efficiently. I don't think there's a fixed target, but obviously you want to go as low as possible. And probably the human brain efficiency is a good reference point for how efficient we want to be.
Okay, thank you very much.
Thank you.
Then let's thank the speaker again.
Thank you.